me just make sure it's recording real quick. Give it a second to load so I can see here. There we go. All right, got some confirmation. Let's talk about computational phonology. So in the previous unit, we learned how computational methods like formant tracking and simulating the vocal tract can help phoneticians better understand the acoustic and articulatory mechanics behind language. That was sort of our main first real linguistics lecture, right? We also learned how phonetic data can be used in more practical ways in our second lecture for computer applications like speech to text and text to speech and things like that. In last week's Python lecture, we learned all of the tools you needed to do your first project, that vowel plot project. So you learned how to use prot to measure vowel formants, you learned how to read files in with Python, and you learned how to plot data with Python. Now that we understand how computational methods can deal with the raw sounds that languages use, we're going to begin our unit on computational phonology, which is the study of how computers can learn the patterns that sounds actually follow in various languages, right? So we learn about kind of understanding the sounds and how they're created and how they're kind of physically implemented in sound waves in the phonetics unit. Now we're going to take those sounds and learn about how they're ordered and things like that. So first, let's introduce the idea of phonotactics. So when I said we're going to learn about computational phonology, that is a kind of a very large umbrella. There are a lot of different kinds of sound patterns. The first kind of sound pattern we're going to be learning about in this class is phonotactic sound patterns. So let's talk about what those are. If you give a word to a speaker of a language, they can usually tell you at least two things about that word, just based off of the way the word sounds, right? So they don't need any other information. You just say the word out loud, and they can probably tell you whether that word is in their language or not, right? So obviously no speaker is going to know every word in their language, right? Nobody has a perfect vocabulary. But generally speaking, you'll be able to say, oh yeah, the word bat, that's in English, or oh yeah, the word hola, that is in Spanish, or something like that, right? But you'll also be able to say, or a speaker would also be able to say, whether the word can be in their language. So if it's not already in the language's vocabulary, does it sound like it could be? So for example, an English speaker is usually going to tell you that brick is already a word in English, right? They're those red rectangular things we build buildings out of. They could also tell you that blick isn't probably a word in English, right? But it could be. There's nothing about the sounds in blick that make it sound not English-like. It sounds like a perfectly fine English word. As opposed to bnick, B-N-I-C-K, which isn't a word in English and doesn't really sound like it could be one, right? Words in English don't really start with B-N. So whether a word is in a language's vocabulary represents knowledge about the lexicon. So lexical knowledge is just knowledge about the list of words in a speaker's mind, right? You could think of the lexicon as sort of your brain's dictionary. The second piece of information, that information about whether a word can be in a language, is knowledge about the language's phonotactics. And phonotactics are the sound patterns that the words in a language's lexicon follow. So the kind of like rules and restrictions that say, this is what a word in this language sounds like. Any new words that are added to the lexicon have to also follow those phonotactic rules. So there are a lot of common phonotactic patterns across the world's languages, and oftentimes a common phonotactic pattern is going to be called a natural pattern. One kind of natural pattern is banning syllable final consonants. So an example of a language that follows this pattern is Hawaiian. So native Hawaiian words don't have any syllable final consonants. So if you take a word like aloha, right, all of those syllables have consonants, if they do have consonants, at the beginning of the syllable. That L and that H are at the beginning. They're not allowed to be at the end. Words that are borrowed into Hawaiian are also like this. So like the word for computer, because computers were invented relatively recently, was borrowed into Hawaiian from English. And so you get this word kamepiula, something like that. I mean, I'm sure I'm pronouncing that somewhat wrong because Hawaiian is not my native language. But the important thing to notice from there is, again, all of those consonants end up at the beginning of a syllable, even though the word computer in English has that M at the end of its first syllable and the R at the end of its last syllable. Those end up getting dropped when it was borrowed into Hawaiian so that the word computer would follow the phonotactic patterns of Hawaiian. Another common pattern across the world's languages is called sonority ordering. So this is a phonotactic restriction that controls the order of consonants within a syllable. And it says that the most vowel-like consonants should appear closer to the syllable's vowel, and the least vowel-like consonants should appear away from the syllable's vowel. And exactly defining what I mean by vowel-like there gets really complicated. This isn't really the class for that. But we have this in English, so hopefully you can get a kind of intuition just from some examples here. So a made-up word like grolk maybe sounds a little weird, but it's okay in terms of English's phonotactic rules. But if you had a word like rgolk, where you have the R coming before the G in that syllable, that's going to be pretty bad. So is a word like grokla, where you have the L coming after the K. Both of those don't really sound like okay English words, and that's because R and L are very vowel-like consonants. So both acoustically in the sound wave, they're very similar to vowels, and in articulatorily, how you pronounce them in your mouth. And so in English, our phonotactics want the R and the L to be closer to that O than the G and the K, because G and K are less vowel-like than R and L are. So that's an example of sonority ordering. One of the most common kinds of phonotactic patterns is called assimilation. And this is when sounds in a certain context have to be similar to one another along a particular dimension. So we have examples of this in English as well, but just to kind of pull in another language as an example here, in Turkish, all of the vowels in a word have to either be made in the back of the mouth or they have to all be made in the front of the mouth. You can't mix front and back vowels in the same word. And they have to all either be made with rounded lips or all be made with lips that are unrounded. So all the vowels in a word have to either be round or unround. Or round or, not round is how I should say it. So they've got this assimilation restriction in their phonotactics that says, hey, all these vowels need to match along the dimension of backness in the dimension of roundness. So moving on here, learning more about phonotactics. So far, we've only talked about speakers' categorical knowledge of which words can or cannot be in their language. But phonotactic knowledge is actually more fine-grained than just categorical judgments. Speakers also know whether a word is likely to appear in their language. So not just if it is or isn't, or whether it can be in their language or can't, right? They also have this knowledge about whether it probably could be in their language or probably not or definitely not. They've got different degrees of judgments that they can dole out when they're given some word that they've never heard before. So, for example, words beginning with KW sequences like quick or queen are relatively common in English. We've got tons of words that start with qua. So a novel word like quib would be rated as very likely, right? People would probably be perfectly happy to borrow the word quib into English. But words beginning with GW sequences, like the name Gwen, are relatively rare. So novel words like gwib would be rated as like maybe a little unlikely, a little weird sounding. Not completely impossible, right? We've got words like Gwen, but gwib just wouldn't be, I think, quite as a well-rated word as quib. And hopefully your judgments are kind of matching with what I'm saying here. But in case you're having some doubts, stuff like this has been shown like experimentally. So I'm not just kind of pulling this out of the air. These are facts about English speakers' judgments. I'm not just getting them out of my head. But then this last example here, WK initial words, those are completely absent from English. So speakers are likely to think that a word like wukib is completely impossible. So this is what I mean when I say that speakers' knowledge of their phonotactics is pretty fine-grained. They can tell you the difference between a novel word that sounds like it absolutely could be perfectly common in a language a novel word that sounds like, it might be in this language, but if it was, it's got this kind of rare sequence in it, and words that have completely absent sequences, words that are completely impossible. And we call that gradients, right? They can judge words in a gradient fashion. And sometimes this gradients in speakers' judgments can be a little hard to represent in theories of phonological grammar. So I'm going to be kind of abstracting away from the history of this idea of how to best kind of analyze phonotactic patterns in these slides. We're going to skip instead to one popular approach that can handle this gradients. I just want you to know that like it took us a while to get there. It was a little hard to kind of figure out the right way to make our theories of phonotactics as fine-grained as people's actual judgments. So now let's talk about how we do that. How do we represent phonotactics? And we're going to be using something called a constraint to do that. So a common way for linguists to represent phonotactics patterns is with what's called a constraint-based grammar. You'll sometimes see these called optimality theoretic grammars too. You don't have to know that term for the exams in the class or anything like that, but if you see it in the readings, that's why. It means the same thing as constraint-based. The kind of grammar that I'm going to be talking about was kind of originally formalized in the early 90s. So I guess about 30 years ago now. But it wasn't really a popular approach for phonotactics until around 20 years later. So like the late aughts, around like 2008. A constraint-based grammar uses constraints to say what kinds of sequences or sounds aren't allowed in a language. So typically in a constraints name, we use an asterisk symbol to indicate that whatever's being described is not allowed in that language. And there's also another symbol that's helpful to know, this hash symbol. Some people call it like a hashtag or a pound sign. That represents either the start or the end of a word, usually when it's in a constraint. So constraints like this can be very general. So there's this constraint star coda or asterisk coda. And that means that no consonants are allowed at the end of a syllable. So syllable final consonants are usually called codas in linguistics. So you say asterisk coda to say that this constraint means the language has no codas, no syllable final consonants. Agree back is another nice like kind of general constraint. So this says that all vowels in a word have to agree in their backness. So this is like that Turkish example I talked about before, where all of the vowels in a word have to be a particular kind or similar in a particular way. If they aren't, then they violate this constraint. You can also have really specific constraints though. So you could have a constraint like asterisk H hash symbol. And what that is saying is don't have H sounds at the end of a word, right? Remember the hash symbol represents either the start or end of a word. Since it comes to the right of the H here, it's the end of the word. And so we're saying that we don't like it when a word ends in H. This constraint is violated by that kind of construction. This other constraint, same thing, it just goes in the opposite direction. So asterisk hash angma, that ng kind of hybrid symbol, which stands for the sound at the end of the word like thing. What this constraint is saying is to not have ng sounds at the beginning of a word. So now that hash symbol is to the left of our sound. So it's standing in for the beginning of a word. And the asterisk, again, is saying like, hey, this thing I'm about to describe is a thing that this constraint does not want you to have. So remember the feature systems we talked about last unit, right? That was what your reading was about. It was a kind of chunk of our phonetic slides. We talked about those phonetic features and how they help us group together sounds that share phonetic characteristics. So, for example, the sounds ma, na, and are all considered nasals because you release air through your nasal cavity when pronouncing each of them, right? The way we would write down this feature-based group is plus nasal. That's something we didn't talk about a ton last unit. And what this kind of label, plus nasal, is telling you is that we're talking about the feature nasal, and plus means that the sounds we're wanting to describe are nasals. We could also say minus nasal, and that would be saying sounds that aren't nasals, right? So we've got a plus and a minus that usually come right before our feature label, And those just help us say this is a feature that we want in the sounds we're talking about, or a feature that we don't want in the sounds we're talking about, right? So features like this are really helpful when writing constraints, and that's because the sounds that pattern together in phonotactic patterns are often similar to one another along one or more of those phonetic dimensions. So that Turkish vowel assimilation I mentioned before, you can use constraints like agree back and agree round, where back and round are these like commonly used features. You can just kind of pull those and use them both here for Turkish and for a lot of other languages, a lot of other patterns in a lot of other languages. So typically, if you're using more than one feature to describe a single group of sounds, so let's say I don't just want nasals, right? Let's say I want nasals that are also made with the lips. So I might say plus nasal plus labial or something like that. If you want that, you're going to enclose those features in square brackets in your constraint and separate them with commas. What this indicates is an intersection of the groups you're describing. So if I say plus round minus back, and I've got them separated by a comma and inside of square brackets, I'm saying that I want all the vowels that are made with lip rounding, since I said plus round, that are in the front of the mouth, since I said minus back. And the constraint star plus round minus back bans any vowels like that. So this is saying don't have any vowels that are both plus round and minus back. That's what that comma does. If there were more features we needed to specify, we would just keep adding in commas and adding in features within those square brackets. And we'd get a smaller and smaller intersection of the possible sounds in the language as we added in more feature descriptions. When a constraint needs to refer to separate groups of sounds, you put those groups' features in ordered bracketed groups. So this constraint I have here, star or asterisk plus nasal minus nasal, since we have these features in different squared brackets, they're representing different sounds in this constraint. So what this constraint is saying is don't have a sound that is plus nasal followed by a sound that is minus nasal, right? So when you've got a comma and a single set of square brackets, we're finding the intersection of these two groups. So this is saying don't have a single sound that is both round and minus back. This is saying don't have two sounds, the first of which is plus nasal, the second of which is minus nasal. That can be a little tricky to keep track of when you first start this stuff. So let's talk about some examples of constraints. So typically a constraint-based grammar is written in a table that shows various real or made-up words in the first column of the table, and then how many times each word violates each constraint in a language in all the subsequent columns. What we call these tables when we're using them with constraint-based grammars is tableau. So that's like just the French word for tables. The person who, or one of the people who helped invent these constraint-based grammars was French back in the 90s. So we call these tableau. So in our first tableau here, we've got brick, blick, bnick, and unic. And here I'm showing whether or not those words violate this constraint that I have in my first row. So what this constraint is saying is asterisk, hash sound, plus labial minus vowel, plus nasal. So let's kind of break that down one piece at a time, right? The asterisk is saying that we don't want to have whatever is described in the constraint name. The hash symbol is saying that we're going to be talking about the beginning of the word, since it's to the left of the rest of the material here. Then our first sound is described in this first set of brackets. Oops, there we go, sorry. This first set of brackets. So our first sound in the description of this constraint needs to be plus labial and minus vowel. So this is any sound that's made with your lips that is also not a vowel. The second sound, our second kind of bracketed set of features here, is just plus nasal. So this is saying don't have at the beginning of the word a labial non-vowel followed by a nasal. So if we come down here in our example words, brick doesn't violate this. It does have a labial non-vowel here, so buh, that's made with the lips and it's not a vowel. But the next sound after it isn't nasal. It's just an R. R's aren't nasal. You don't release any air out of your nasal cavity when you say the sound R, so we're good. No violation here of our constraint. Next up, blick, same thing. B is a labial non-vowel, but L isn't nasal either. When you say la, you're not releasing any air out of your nasal cavity. Next up, BN for bnick. This does violate our constraint, and it violates it once, so we put a 1 here in this cell of the tableau. And the reason it violates it, right, is because at the beginning of our word, there's the hash symbol, we have a labial non-vowel, our B, and we have a plus nasal sound following it. So that BN sequence violates our constraint here. So we get 1 violation for that. Our last word here, unic. So oo, that vowel, is made with the lips. You round your lips with it. So arguably it is plus labial, but it's not minus vowel. Oo is a vowel. So this doesn't violate this constraint because of that. It does have a nasal after it. It's got that in there, just like bnick does. But because we've got an oo, unic could be a perfectly fine word in English. At least according to this constraint, right? If this is our only constraint we care about. Next example over here in the bottom right goes back to that qua, gua, ug stuff we were talking about. So I've got 2 constraints here, gua, or I guess star gua and star wug. And our word quib doesn't violate either of those constraints, right? This is one of those specific constraints, right? We aren't using features here. We're just specifically saying the sequence ga wa is bad and the sequence wa ga is bad. So qua doesn't violate either of those. Gwib violates the gua constraint, but not the wug constraint. And wugib violates the wug constraint, but not the gua constraint. So we've got 1 here for that one, 1 in this other column for that one. And if we had more constraints, we would just add in more columns here. Our last word here, gwip-gwib, has 2 violations of our star gua constraint. So you can see here, you go through, you find that gua, that's a violation. You find this gua, that's a violation. And you just keep on adding as many as you need. As many as you count in the word goes into the cell where the word and the constraint intersect in our table. So this is generally speaking how constraint-based grammars are going to work. And anytime you're doing something with phonotactics, or really any part of phonology, so remember phonotactics is sort of one subdomain of phonology as a whole. Anytime you're doing this in real life, you're trying to read an actual research paper in this domain of linguistics, you're probably going to be reading something about constraint-based grammars like this. So it's really good to be familiar with them if you're interested in this kind of thing. All right. One more thing to talk about when we're talking about constraints is that constraint-based grammars have also been used to analyze the phonology of sign languages. So the phonetics of sign language, remember, we've talked about how we weren't talking about that a couple weeks ago. So I talked about how there just isn't a ton of computational phonetic work on sign language. And then we talked a little bit about how some of the practical sides of computational phonetics have intersected with sign language. There is a decent amount of phonology done on sign language, including some computational phonology. And so there are constraint-based grammars that have been made for various signed languages. So this particular example I'm showing you here is Russian Sign Language. So there are some constraints here. There is a speaker of Russian Sign Language saying a sentence, or I guess part of a sentence, a phrase maybe. And we've got constraints here on the left of our tableau. And instead of putting the number of violations, they're just putting asterisks in this table cells to show which of these sentences violates which of these constraints. There's a lot here that you don't know enough to understand yet. Don't worry about that. The main purpose of this example is to just show you that constraint-based grammars aren't specific to a particular modality, right? So the constraints we're going to use are different than those used in spoken languages, since the phonetics of sign language are different than the phonetics of spoken languages. And the features in those constraints are also going to be different, but there are a lot of similarities. So the kinds of representations constraints favor, the kind of processes they encourage are pretty similar between sign language and spoken language. So an example of this is that assimilation also exists in sign language. And the kind of constraints that motivate that in a constraint-based analysis are going to be pretty similar between spoken language and sign language. So constraints, very widely used in phonology, regardless of what modality you're using. Now let's talk about an actual implementation of a constraint-based grammar and how we're going to think about that in this class. So in the example we just went over a couple slides back with gwa and wug, we had no way of showing that the gwa initial words are more likely to occur in English than the wug initial words, right? So that kind of granularity that I talked about a couple slides before that example showed up wasn't present in the example I showed you with the tableau. And there are several ways that phonologists have proposed for making sure that you can put that kind of a judgment into your theory of phonotactics. One is ranking the constraints from most important to least important and kind of having that factor into the judgments that your grammar predicts. Another is giving probabilities to each pair of constraints, and those probabilities just represent the chance that one of those constraints is more important than the other when judgments are being made. And then the last one, the one that we're going to be focusing on today, is numerically weighting each constraint to show how important it is. This is called a maximum entropy phonotactic grammar. It's also sometimes called a harmonic grammar. And this is the approach that we're going to be focusing on in this class. So we'll be talking about it today. We'll be talking about it some in 2 weeks. And we'll also be talking about it in detail during the Python lecture for this week. So over here, I have an example of a maximum entropy grammar using those words from before. So quib, gwib, and wgib. And in our first column, we've got that star gwa constraint, but now we also have a weight showing how important it is for our grammar. It has a weight of 1. Then we've got our star wug constraint, and it has a weight of 3. So what this is saying is that it is worse to violate this constraint than it is to violate this constraint, because this one has the higher weight. So it's more important to speakers of this language. And that kind of jives with the whole thing we were talking about before, right? How English speakers are kind of okay with gwa beginning in a word. Sounds a little weird, but they can do it. Whereas wug just never shows up in English, and speakers are going to rate that pretty poorly. And we can do a weighted sum of the violations for each word. So quib here has 0 total violations or weighted violations. Gwib has 1 total weighted violation because we take the weight 1, multiply it by the violations here, 1, sum all the violations it has across all the constraints, and we just end up with 1. Wgib here has a weight of 3 and 1 violation here, so 3 times 1 is 3. That's how we're going to be weighting our violations, is multiplying the weight by the violation. We sum across this whole row to get the sum of those weighted violations, and we get 3 for wgib. So again, the higher this is here, the worse the word is for speakers of the language. So quib is perfect. It's got a weighted sum of violations of 0. Gwib is 1, showing that it's like okay, but not perfect. And wgib gets 3. How are we going to use these weights, though? What is the specific way we're going to take those weighted sums of violations and actually get judgments out of them? So remember that speakers' phonotactic judgments tend to be gradient, like I was describing before. And that means you can tell how likely a word is to be in a language and not just whether it can be in the language or not. Maximum entropy grammars are a way to convert constraint weights into these kind of word probability estimates. So they assign a probability to all possible words that could be in any language and tell you how probable it is that the word can be used by whatever language's weights you're using. To convert weights to probabilities, we just have to do a little bit of math on them. So first you multiply the weighted sum of violations, that thing we had in the last column, by -1. And we'll call this capital H. Capital H stands for harmony. You don't have to worry about why it stands for harmony. That's just what that is. Then you're going to find e to the h. So e to the power of harmony, where e is a mathematical constant approximately equal to 2.71828. It's the base of the natural logarithm. Again, we don't necessarily need to worry too much about why this is, what we're using. It essentially just puts our values in kind of a nice range if we put the h to the power of the e. Then we take that, our e to the h, and divide that answer by the sum of all other possible words e to the h. So what this is going to do is it's going to show us the proportion that a particular word takes up of all of the words e to the h's with its e to the h. In reality, there are an infinite number of possible words, right? You could always just add one more sound to the end of a word and keep making longer and longer words. So when we're using a maximum entropy phonotactic model, we're always going to assume that words have a maximum length. So like 10 sounds maximum. That's going to make you pretty safe. And in most languages, you won't have many words that are more than 10 sounds long. So now let's actually walk through a full example here. Let's imagine that a language only has 2 sounds, so like G and W, and that words can only be 2 letters long to keep things really simple for us. So like I was saying, we would normally say something like 10 as our maximum length, but here I'm going to walk us through an example, so I want to make sure it's nice and tiny. So we're living in an imaginary world with an imaginary language. It's got the sounds ga and wa, and words can only be 2 sequences or 2 sounds long. And this language's speakers, this imaginary language's speakers, they disprefer the sequence wug, like English speakers, that WG sequence, but they disprefer sequences of 2 identical sounds even more. So we've got a list of possible words, gwa, wug, 2 W's and 2 G's, and we want them to be rated in likeliness in that order. So we want gwa to be the most likely word, WG to be a little less likely, and then these 2 to be the least likely, WW and GG. These are the ones that the speakers like the least. So our maximum entropy model is going to assign probabilities to all of these words, representing how likely each one is to appear in our made-up language, right? That's what maximum entropy grammars do for us. So we've got all of our possible words here in our first column, and we've got 4 constraints here in our first row. Our star WG constraint is going to have a weight of 1. We've got a star GW constraint, and it's going to have a really low weight, 0.01. It's hardly even there. Then we've got our star WW. It's got a weight of 3. And our star GG, which has a weight of 3 as well. So these constraints are the most important. This constraint is somewhat important, and this constraint isn't important at all, really, to the speaker's judgments. So here, GW is going to violate this one, the unimportant one. So its H value is going to be the sum of all of its weighted violations times -1. So 0.01 times 1 is 0.01, times -1 is -0.01. That's its H. WG violates this constraint, which has a weight of 1. So 1 times 1 is 1, times -1 is -1 over here. WW violates this constraint, star WW, which has a weight of 3. So we're going to take 3, multiply it by 1, multiply that by -1, and get an H of -3. And then our last row here, GG, same thing, weight of 3 here in the constraint it violates. 3 times 1 is 3, times -1 is -3. Again, if one of these words violated more than one constraint, you would just sum those weighted violation counts across the row and multiply that whole sum by -1. This is just a simple example, so each thing is only violating one constraint. Once we have our H's, we can do e to the power of each H. So it's going to give us 0.99, 0.37, 0.05, and 0.05. Then we take the full sum of all of these e to the H's and divide each value by that sum. So that shows us the proportion of the sum that each of these take up. So this one takes up 0.68, this one takes up 0.25, this one takes up 0.03, and this one takes up 0.03. And we treat those proportions as the probability of that word occurring in the language. So GW has a relatively high probability of 68%, 0.68. WG has a much lower probability, right? But still a decent chunk of the overall probability mass. So 0.25, right? There's a 25% chance you've got WG as your word. And then we've got 3% for each of these last two, showing that they're pretty dispreferred. Speakers of this language do not like WW and GG. So that's a full maximum entropy grammar demonstrating these facts for us. But how do you actually get these weights, right? How do linguists decide what weights each constraint should have? And if people actually have this inside their head, right? If there are weighted constraint-based grammars inside a child's mind, how is the child learning their language that way? How are they finding the right weights for their grammar? So to do this, we have to imagine the maximum entropy grammar as a sort of mathematical function that maps from constraint violations and weights to a set of word probabilities. And then we can look at those word probabilities that we get from our grammar and compare them to the actual word probabilities in the language that the child is learning or that the linguist is analyzing. And you can use the difference between those two probability distributions, the probabilities that the grammar gives you and the probabilities you actually see in the set of words in a language. And the difference between them can be used to make each weight either higher or lower, depending on what's going to cause a closer match to that data in the language. The precise math to do this requires calculus, so it's outside of the scope of this class. But in this week's Python lecture, like I said, we're going to be talking about maximum entropy grammars and how to make them in Python. And so I'll show you a fun little shortcut there that lets you find decent weights without having to do any of that math yourself. It's essentially just built into a thing you can download for Python pretty easily. And actually, we're using Colab, so it's already installed in Colab. Already right there, ready to use. So that's how you get the weights for maximum entropy grammar. If you know lots of calculus, you've taken the first 3 or so semesters of calculus, you could do this math and just find it yourself by hand. Most people, though, are going to be doing something more automated. All right. So that is the end of the linguistics lecture for this week. Like I said, this week's Python lecture is going to be about making maximum entropy grammars in Python. So if you haven't done that before, which I suspect no one probably has done that in Python before, even if you are familiar with Python, I definitely recommend watching the Python lecture. We're also going to be having a lecture there very soon that will... No, I won't preview that. So yeah, just check out the Python lecture this week. And keep an eye on the assignments that are due as well. And email me if you've got any questions. All right.